So this is a presentation of the work we're doing at Archaeoscape. And it's going to be a little bit about what is LiDAR archaeology, first place, what is Archaeoscape, and our recent submission, which was accepted at New conference, which presents our data set called also Archaeoscape. So just to present our team a little bit, basically Archaeoscape and the previous work on LiDAR archaeology was all due to Damian Evans, who has been the director of this project and developing the approaches for 12 years already. He passed away last year, and we had to continue without him. The work which I'm presenting here is going to be a lot of it basically what we have managed to do in this year 2024, but also I'll do a little bit of background what we've been doing before. So yes, this work we have been doing with Christophe Potier, who is now the new supervisor of the project. Very, very good to have an archaeological supervisor. And we're also doing collaboration with INPC, National de France, which very good to have people who know machine learning very well. And me, I'm the co-director, so I have a PhD in machine learning. It helps also. So anyway, why and what is even LiDAR archaeology? When we go into the field in Asia, or actually anywhere, but let's say in Asia, we have the issue that a lot of the ancient remains, they're not there anymore. They're done with perishable materials and they disappeared. So we can still see from the satellite images, some of them, but then they're kind of subtle. Here's one example. Let's do. So, talking about subtle and fine topography changes. If we go on the field to look at the remnants of the ancient settlements, often it looks like this, so you don't really see much because the changes of elevation done by the ancient people 1,000 years ago, they have most disappeared. They have deteriorated, and then we have local anthropological changes. You know, people like to have agriculture, for example, destroys things. And also we have vegetation. On one hand, it obscures the archaeological features, which makes them hard to see. On the other hand, it's good to have vegetation because it prevents the local people from doing agriculture. So basically, if you want to be able to pick up the archaeological landscapes, the archaeological topography changes, you want to have something which can pass through vegetation and which can pick up these subtle elevation changes. And here comes the LiDAR. So what we have been doing is the aerial LiDAR. As in, you put a LiDAR scanner on top of the aerial platform. Can be plane, helicopter, or a drone. Plane works the best. And then you fly over large, and it's great to have aerial platform like, again, plane or helicopter because you can really fly quite big areas. And the trick, is it not working? No. Okay. So the trick here is LiDAR is basically lots and lots of millions of little laser points, which can, which they shoot from the aerial platform, and they pass through the vegetation. It's not that they can actually penetrate the leaves, but when you are in the forest, unless it's some kind of very, very dense forest and you are in under the canopy, you mostly have light inside. And if you shoot millions of your laser points, some of them penetrate and they reflect back to the aerial platform and you get points. So it would look something like this. So this is a cross-section of the LiDAR scan. As you can see, most of the points, they actually the leaves and the vegetation and the canopy and the undergrowth. But then some of them actually penetrate. They form the outline of the topography, the land, the earth. And if you remove 90% of the data, you end up with your topography. And this is very good because then you can analyze the ancient traces. And this would look something like this. So this is a Campus Y in Cambodia, very monumental temple complex. If you look at it from satellite, you can actually see the outer, well, the outline of the temple, but it really helps to have the LiDAR scans, because then you can see much more. You can see a lot. And if you spend months, I would say 6 months, maybe 1 year, 2 years to annotate and field verify what you have, you end up with a map like this. So this is the map where we have annotated the remnants of the occupation mounds, the barrays, the little lakes, the archaeological features in all their variety. And it's pretty cool. So one example is Cambodia Angkor Wat is famous temple, I guess. This is how it looks like from a satellite. If we look at how it looked like before the LiDAR scans of Damian Evans, the archaeological maps and features, they look roughly like this, because a lot of it is covered by vegetation. And after the campaign of Damian Evans in 2012, and annotation which took years, but it's very meticulous annotation, we end up with something like this. Big difference, right? Doing this by just field verification without LiDAR, it would be impossible, I have to say, because a lot of the features are very subtle. But even this annotation, it takes time. So now that you have been briefed on what is LiDAR archaeology, is doing maps like this and exploring under the canopy, let's talk a bit about what does Archaeoscape do. And Archaeoscape follows the 3 very basic axes, which is acquiring data, interpreting the data, and aggregating and sharing the data, which is, well, I guess science, right? So acquiring the data, something which we have been doing a lot of. And this is a section of acquiring the data. So in the previous 12 years, we have been working on mostly Cambodia and the Khmer heartlands of the ancient Khmer Empire, as a center of course, Angkor Temple complex. We had extended we had a huge extension into the Laos area with the Champa project, which was in 2020, 2025, but it's still the Khmer Empire, which is good because you have ability to gather a lot of the corpus of similar data and similar culture. What we have done this year, and this was actually the Archaeoscape project, so initial goal is to extend further into rainforest civilizations as a whole. We started small, just with whole of Southeast Asia, and then we had the very unfortunate circumstances which made us limit our acquisitions. So in 2024, basically we had the ERC came and said, you have to finish the project. And in April, we finally got our money frozen, and we had until September to do anything we wanted to do. This is very, very short on the scale of archaeological acquisitions and the scale of LiDAR campaigns. Usually you have to prepare them for at least a year before. Luckily, we have managed to do 2 acquisitions following the original Damian Evans proposals. One of them is in Sukhothai, which is still somehow Khmer Empire. So this is on the outskirts of the Khmer Empire, but there's also an interesting thing that Sukhothai is also the birth of Siamese culture, Siamese nation. I'm not an archaeologist, okay? So we are still kind of on the Khmer periphery, but we are going now into a different culture, influenced by Khmer. And then we have another acquisition, which is really have nothing to do, nothing to do in common with Khmer, except it's also in tropical forest. And this one is in East Java, Indonesia. It's in volcanoes, very, very cool, but very, very different. So altogether, we have maybe 900 kilometers squared this year, and the results which we got are very preliminary. I'm just going to tell you how it works usually as a LiDAR campaign. So first you do your aerial acquisition, so you fly the platform, you design the parameters, how the plane is going to, yes? How the plane is going to fly, you have to do preliminary acquisition, but it's actually pretty fast. Then there is analysis function. This is where you would need IT people who, well, this is my part, I would say. Interpretation of the features, processing of the points, all the cool stuff. And then there is the most difficult part, which takes years, is the archaeological follow-up. So first you do the acquisition, then you do the analysis of the points, and then you do the follow-up, which involves, most importantly, the local authority engagement and collaboration, which is the hardest part. Once you have that figured, you have your MIUs and also documents in place, the people like you, you can actually go on with field verification and mapping and then publish this. So just a few things what we have done in 2024. We had covered some locations with UAV. UAV is great if you want to cover small areas which you want to pinpoint. If you want to extend to larger areas, basically it helps to have an aerial platform like a plane. So we had done acquisition in Thailand, Sukhothai, some very preliminary pictures, and you see Christophe Potier handing over the data to the local authorities. Very important. We are working in a different country, so the local authorities have to have a copy, and they have to be involved and asked basically during all the steps. And here is a very preliminary data from the East Java, Indonesia, where we have scans from 2 volcanoes. One of them is active, with spewing ash while the plane was flying. We found for this, I would say for very, very preliminary, we found hundreds of archaeological features, which look very, very promising, but such preliminary work that we have nothing to present to you yet, but I have a picture of me on the mountain. So yeah, it's very nice. Mountain completely covered in archaeological features. It's nice to have stacked mountains. You have to hike up though. So data analysis and interpretation. So usually what you would do is you would have your archaeological map, you would remove the vegetation, and you end up with topography, so the elevation of the ground, which tells you a lot about what has been happening on this land the last thousands of years. And the next part is to annotate the features which you see on the topography. This takes a while. So what we have been doing is we had people who have been very good at this, specifically Adam Weicker, who's been annotating in QGIS, so the GIS products manually, all these features, which requires you to be very good at interpreting what you see on the map, being able to sit without and in front of the computer, like days after days, months after months, clicking, 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 but it gives you good results, though it's kind of slow. But they are the best results. So we have an issue that if you have 2 people doing annotations, you might have different annotations. So it becomes more difficult because you have to design protocol for annotation to be the same. If you have people leaving, because you can't expect PhD students for that long, eventually as they graduate, well, again, you have a loss of continuity, and just it's very slow. It takes time. We have acquired 7,000 kilometers squared of the data. We have by now had half of it annotated. So 12 years, 7,000 kilometers, only half of it has been annotated. Takes time. So what we can do is, well, I have a machine learning PhD, so I guess we should do some machine learning. Here is a picture from a long time ago. Hope you can interpret it. Basically, the ground truth is the part on the left, and this is the annotation which was done by our PhD student. Been working on this for a while. This is the center of Angkor Thom. And on the right, there's a green line, which I hope is visible. but everything inside this square is a prediction of the machine learning model. It's not perfect. You see, it has some artifacts, it has hallucinations. For example, this is one huge bar, right? This is one big lake, and somehow the model predicts that there is no water inside. Now there is no water, but it used to be. So semantically, yes. So basically, semantically, it's a bit of a difficult problem because the model has a small assertive field, you have to account for it, and there are imperfections. But as a start, if you annotate very well part of your data and you just extend the annotation to the side, works very well. If you try to extend annotations on a completely different area, which has different elevation profiles, or, God forbid, different culture, becomes more difficult. That's why we have machine learning. We have a lot of work for the machine learning people. And one more application, which is simple application. For example, we could do river network delineation. There is the mountain north of Siem Reap, north of the Angkorian complex, which contains the ancient capital of the Khmer. And it also contains a lot of rivers, and it's mountain, it's covered in forest. And if you want to follow up some things like people living in isolation, there are hermitages. They're not very visible on the LiDAR because, well, it's not a very big change in the environment, but you can get it based on the secondary circumstantial evidence. One of them would be people living in the mountains. They still like to drink water, right? So probably if you follow up the rivers, you are more likely to find something. So this is a very simple thing which we have spent maybe 1 hour on just to predict the river networks in Kolean. Works pretty well. And one more application is region hole identification, which is actually routers are everywhere. There's a lot of work on that and should be researched, but especially in Cambodia, there's a civil war and people have routed a lot. So one thing that helps us, because if you find the mount, on top of the mount, there is a hole, routing hole, most likely this has been a temple or some kind of features, so it helps us. On the other hand, we would like to be able to identify these routing holes everywhere, make a map, and maybe later revisit, do a study on it, help to trace artifacts. So routing hole identification is something which is very easy to do with machine learning because the holes are pretty specific and they don't require so much of context. That's one of the logic we have. And there is lots of different applications, biodiversity quantification, biomass estimation. There are interesting relations we can drive between the archaeological remains and the local forest. So ancient influence of the ancient people on the current vegetation, which is something actually there. And all sorts of other applications. So again, if you're a machine learning person, you have this data, you have so much work to do. And now, aggregation dissemination. So basically, you have a lot of data for different countries, and 800 kilometer we acquired just this year. This is how it looks like, kind of at scale. As you can see, the top right part is a Laotian acquisition, very big one. Then we have the ones at the bottom. This is the acquisitions which we did just in this year. It's a lot, basically. And of course, you have a lot of data. It's very nice. You can do all sorts of machine learning, but there are challenges. First of all, is how to properly consolidate the data. If you really want to interpret the data well, you have to consider archaeological context. So it's not just what you see on the map, it's also the field data, the historical maps, surveys. People have been working in this area for 100 years at least. Well, if your has existed for 100 years, so you want to kind of interpret what you're seeing on the map, taking into account all this data. And of course, you want to have the temporal aspect because the environment it evolves, and the roads and the map which you had done in 1960, it's not going to be relevant to what you're doing now at the same level as the map which you have done yesterday. it's hard to integrate the data because heritage management lies with the local authorities. Local authorities don't like Europeans coming to their country, taking scans and just taking it away and working on it by themselves. You have to make sure that they are always involved. You have to consider the very important question of data sovereignty. Again, it's their country. And it's also one of the reasons why open data is not embraced in archaeology. Besides, archaeologists don't like to share. It's not the real reason. It's a big reason of just this sort of baggage, legal baggage, and well, just data safety and sovereignty. Finally, there is one thing is there's no such thing as free storage. So if you have terabytes of data, and then the European Research Council in their infinite wisdom decides to cancel your funding, you end up with a lot of data, which has taken years to acquire and millions of euros has been spent on it. But it can get lost. It can be corrupted if you just store it with your modalities, without any funding. Difficult, especially if you cannot have a Creative Commons license, so it's not really open data. You face challenges, and we tried to address some of them. So one thing which we have done is a WebJS platform, which is an open source thing which we are developing. We should be finished very, very soon. So basically, it allows us to integrate multiple modalities. For example, the maps at different levels, different historical layers, and inventory of the sites. And you can access data in the field. And most importantly, you can allow collaboration between research groups. So you can allow different research teams to interact on some part of the data, but not on the other parts of the data. For example, the Thai authorities don't want the Laotian authorities to have access to the same data. Politics, basically. So that's one thing. And second thing is, what you can do is you can release a machine learning dataset. In this case, since you don't actually need georeferencing for the machine learning to predict your features, you can get away with some things. So you can release some of the data which will allow you to train learning models without actually connecting your data to the real locations, which is a bit easier, legally speaking, and it's more palatable. So very quick, I'm sorry, I'm maybe behind my time, but Archaeoscape machine learning dataset for LiDAR archaeology. This is the one which we have released, which got accepted at NeurIPS in the dataset track. Well, the first open access dataset LiDAR archaeology. So a quick overview, we have these 3D point clouds, we remove again the trees, we end up with terrain model, which is a DTM. So for every pixel, you basically have elevation, and you have annotations, which you share as vector annotations. And this is let's say 900 kilometers squared. So it's not all of our data. This is the data in a very specific region in Cambodia, which has very specific consistent annotation and focused on the core of the Khmer Empire. Again, largest, okay, quickly, it's Khmer civilization, center in Angkor, and same thing which you have just seen, large complexes, hydraulics, Khmer Empire, they did a lot of hydraulics, they did a lot of reservoirs and canals. And again, this is perishable traces. Good to see on the ground. Cambodia around Angkor and Siem Reap. Mapping has been done from 2015 to until now. So you would say this is, let's say, 8 years of uninterrupted work and build on the previous work. And basically, we have a lot of different feature types, but for simplicity, and because it's really hard to have multiple feature types, especially in terms of just semantic meaning and machine learning, we have not gone beyond 4 types. So we have temple size, we have origin features, so this is the mounds and the sorts of long walls or the path basically, let's say anything elevated, which is a temple. And we have water feature. So anything which is water. This can be big barrage, can be a small lake, or a canal. And the biggest class, which is background. Annotation, again, QGIS, high definition features, and you have to ground verify. So basically, the dataset has been ground verified over almost a decade. So we are mostly sure about our annotations. And yes, comparison to existing ones, basically nobody puts their lighter datasets in the open access. It's difficult. Read it. So yeah, please use it to train your models. The inputs are 50-centimeter DTMs and orthophotos. And basically what we're doing is splitting the semantic segmentation over these 4 classes: mount, water, temple, and background. Yeah, so some benchmark results is basically we tried the basic things which you see in ants, and they kind of work. I mean, the first example which you saw extending the anchor, this was Plopy tree, I think the standard thing. And of course, if you want to publish at MURIPS, you have to show the latest models. And of course, we had tried the VAT. So this is 3 years ago with the latest, but now it still kind of holds. If you just apply VAT, even if it's pre-trained on your Rhino V2 or this fancy big datasets, it doesn't work so well because the data which you've been training on is natural imagery, right? And we are working on the DTMs, which is the elevation. So with pre-training, the fancy models don't help so much. What helps is the hierarchical models, which is hierarchical VITs like SWIN or BCP-V2. Once you constrain your model a bit more complex, but it does require less data for fine-tuning, you get better results. So basically, if you don't have enough training corpus, try to do some fancy things with your model. It will look ugly, but it will work better. And finally, well, the best thing you can do is you can increase your input size so that you have more spatial context, and that works better pretty much all over the board. Of course, if you continue increasing it, you end up with memory problems, and then you start overfitting also, and you have to have specific algorithms, specific models to account for that. We're working on that. Stay tuned. And the qualitative results, you can see that, well, they're not perfect. Basically, the first result which you have seen, the one which contains just extension, works well because you're continuing training on the same region on which you have just, you're continuing evaluation on the same region on which you have trained just on the side. But if you train on spatially separate regions, you end up having difficulties. This is specifically, well, first line you see the predictions in the center of Anchor, which is fine, whatever you do, UNet or PVTV2. Second one is fine also, but you see the issues with this small receptive field, which cannot predict the inside of the lake because it doesn't see that it's inside the lake. And the last one is a very difficult issue in the suburban cook because you have lots of elevation changes and it's kind of very hilly. So if you train on the flat areas and you go and you test on the hilly areas, it has problems. So you need more work. But anyway, it's just a benchmark, and once you finish the dataset, people are going to with better proposals and hopefully solve the problem of machine learning mapping from the, well, just from the point of machine learning models. And this is it. This is the whole presentation.